Hello there. Tonight, you are not just listening. You are stepping into something far greater than yourself, far beyond the noise of the world, beyond the weight of your thoughts, beyond even the stars above you. There is a story unfolding, a slow, silent story that has been written across billions of years, a story about everything that exists, and how one day even that will begin to fade, not in chaos, not in fire, but in silence. The universe does not rush toward its end. It drifts, it stretches, it cools, and in that quiet unfolding, there is something deeply humbling and strangely peaceful. Tonight, you will journey through that future. You will witness stars dimming into darkness, galaxies drifting beyond reach, and time itself becoming something almost unrecognizable. Each truth will take you deeper into the stillness, where the universe slowly lets go of everything it once was. So allow your body to relax. Let your breathing slow, and let your mind drift into the vastness. If this kind of journey speaks to you, take a quiet moment now to subscribe to the channel and gently like the video. It helps the space grow, so more people can find calm, curiosity, and rest in the same way you are right now. No rush, just a small, quiet action before we continue. Now, close your eyes if you wish, and step with me into the end of the universe. Chapter 1. The Slow Fade of Starlight. Hello there. Tonight, as your thoughts begin to soften and the world around you grows quiet, we gently drift outward, beyond the familiar glow of Earth, beyond the comforting warmth of the sun, and into the vast, slow-moving story of the universe itself. A story not of sudden endings, but of gradual fading, where even the brightest lights, given enough time, begin to dim. The universe, as we understand it today, is not static. It is expanding. This expansion began around 13.8 billion years ago in what we call the Big Bang, and ever since that moment, space itself has been stretching. Galaxies are not just moving through space. They are being carried apart as space expands between them. And here lies our first quiet truth. The farther a galaxy is from us, the faster it appears to be moving away. This expansion is not slowing down. In fact, it is accelerating. A mysterious force we call dark energy is pushing everything apart faster and faster. It is subtle, almost imperceptible on human timescales, but across billions and trillions of years, its influence becomes overwhelming. Imagine placing tiny dots on the surface of a balloon, then slowly inflating it. Each dot drifts away from the others. Now imagine that balloon expanding forever. As galaxies drift apart, something profound begins to happen. Light, the very thing that allows us to see the universe, starts to struggle. When distant galaxies move away fast enough, their light stretches, becoming longer in wavelength. This is called redshift. Over time, the light stretches so much that it fades beyond visibility, slipping into infrared, then microwave, then radio waves, until it becomes nearly impossible to detect. This leads us to a gentle but haunting realization. One day, distant galaxies will disappear from view entirely, not because they are gone, but because their light can no longer reach us. Future observers, trillions of years from now, may look into the sky and see only their own galaxy, surrounded by darkness, unaware that countless others once filled the cosmos. Stars, too, are not eternal. Each one is a delicate balance between gravity pulling inward and nuclear fusion pushing outward. In their cores, hydrogen atoms fuse into helium, releasing energy that radiates into space. This energy is what we see as starlight. But hydrogen, like all fuel, is finite. Our own sun, for example, has been shining for about 4.6 billion years. It has enough fuel to continue for roughly another 5 billion years. After that, it will expand into a red giant, shedding its outer layers before settling into a white dwarf, a small, dense remnant slowly cooling over time. Now imagine this process happening not just once, but across every star in the universe. Some stars burn quickly and die young, exploding as supernovae within millions of years. Others, smaller and cooler, can burn for trillions of years. These long-lived stars, known as red dwarfs, are incredibly efficient, using their fuel slowly and steadily. Here is another quiet truth. Red dwarfs may be the last stars to shine in the universe. Long after larger stars have faded away, these small, dim stars will continue to glow, providing the final pockets of light in an increasingly dark cosmos. But even they will not last forever. As time stretches into trillions upon trillions of years, star formation itself begins to decline. Galaxies rely on clouds of gas and dust to create new stars. But with each generation of stars, that gas is used up or blown away. Eventually, there is simply not enough raw material left to form new stars. This marks the beginning of what scientists call the degenerate era, a time when the universe is no longer filled with bright, burning stars, but with remnants. White dwarfs, neutron stars, and black holes become the dominant objects. The sky, once filled with countless points of light, grows darker and quieter. Imagine standing beneath a sky where stars are no longer being born, where the constellations slowly fade, one by one, until only a few faint embers remain. It is not a sudden darkness, but a gradual dimming, like the last moments of twilight stretching on forever. There is something strangely peaceful about this process. The universe is not ending in fire or chaos, but in stillness, in cooling, in fading light. Another fascinating detail emerges when we consider how long this process takes. Human history spans only a few thousand years. Even the age of civilization is a mere blink compared to cosmic time. Yet the fading of starlight unfolds over trillions of years. It is a reminder of just how vast and patient the universe truly is. Even now, as you listen, stars are forming in distant galaxies. New light is being born, but the balance is shifting. Over immense stretches of time, the creation of new stars will slow, then stop. And when that happens, the universe will enter a new phase, one where light is no longer renewed, only remembered. As your mind drifts deeper into this quiet journey, consider this. Every photon of light you have ever seen, from the glow of a candle to the brilliance of the sun, has traveled across space, carrying with it a story. In the far future, those stories will become rarer, more distant, more faint, until one day they fade into silence. And yet the universe continues, not with brightness, but with a slow, steady whisper of time itself. As we continue drifting through this quiet, expanding universe, the fading of starlight begins to reveal even deeper layers of change, subtle processes that unfold so slowly they almost feel timeless. Yet they shape the ultimate destiny of everything that shines. One of the most fascinating truths is that the universe is not simply losing light, it is also losing contrast. In the early universe, galaxies were closer together, interactions were frequent, and star formation was vibrant. There were brilliant clusters, glowing nebulae, and energetic collisions that sparked waves of new stars into existence. The cosmos was dynamic, textured, and alive with motion. But as expansion continues, those interactions become rare. Galaxies drift so far apart that gravitational encounters, once common, become almost non-existent. Without these interactions, one of the key triggers for star formation begins to disappear. Gas clouds no longer collide and compress as often, and without that compression, fewer stars are born. So the universe does not just dim, it quiets. Within galaxies, another gentle transformation unfolds. Over billions of years, heavier elements accumulate. Every generation of stars fuses hydrogen into helium, and then into heavier elements like carbon, oxygen, and iron. These elements are scattered into space when stars die, enriching the interstellar medium. Another quiet truth emerges when we consider how stars move within galaxies. Stars are not fixed. They orbit the centers of their galaxies over millions or billions of years. Occasionally, these orbits bring stars close enough to interact gravitationally, altering their paths. Over vast stretches of time, these interactions can gradually redistribute stars, causing galaxies themselves to evolve. In some cases, stars may even be ejected from their galaxies entirely, becoming what astronomers call rogue stars. These lonely travelers drift through intergalactic space, far from any galaxy, shining in isolation. As galaxies become more sparse and distant, these rogue stars may become some of the few remaining sources of light in the universe. But even their light is temporary. As time moves forward into trillions of years, the last generations of stars begin to dominate. Red dwarfs, the slow-burning stars we mentioned earlier, continue their long, steady fusion. Unlike larger stars, they mix their fuel efficiently, allowing them to shine for extraordinary lengths of time, up to tens of trillions of years. Imagine a universe lit only by these faint, reddish stars, scattered sparsely across vast distances. Their glow is gentle, almost ember-like, and their presence feels more like a memory of brightness than brightness itself. Eventually, even red dwarfs exhaust their hydrogen. When they do not explode dramatically. Instead, they quietly cool and fade, becoming what some scientists call black dwarfs, stellar remnants that emit virtually no light at all. Though no black dwarfs exist yet, the universe is not old enough. They represent the eventual fate of these long-lived stars. And so, one by one, the lights go out. There is also another subtle process at work: gravitational decay within star systems. Over extremely long periods, the orbits of planets and stars can become unstable due to tiny gravitational interactions. These interactions, though weak, accumulate over time, sometimes causing planets to be ejected into space or stars to shift their positions. In the far future, many planetary systems may no longer exist as stable structures. Planets could drift alone through darkness, no longer bound to any star. These rogue planets would be cold, silent worlds, traveling endlessly through an expanding universe. Another fascinating detail lies in the nature of light itself. Even as stars fade, the photons they emitted continue to travel. Some of this light will cross unimaginable distances, stretching as the universe expands. Over time, this ancient starlight becomes so stretched and diluted that it blends into the cosmic background, becoming part of a faint, uniform glow. This means that even after stars are gone, traces of their existence linger. Echoes of light spread thin across the cosmos. Yet these echoes too will fade. As the expansion of the universe accelerates, there comes a point where regions of space become causally disconnected. This means that light from distant regions can never reach certain observers, no matter how long they wait. The observable universe effectively shrinks, not in size, but in what can be seen or experienced. Future civilizations, if any exist, may find themselves in a universe that appears empty. Without visible galaxies beyond their own, they might conclude that the universe is small and static, unaware of the vast, dynamic history that preceded them. This is one of the most profound truths of all. The universe's past may become unknowable in its future. Even the cosmic microwave background, the faint afterglow of the Big Bang, will eventually redshift beyond detectability. This ancient signal, which today provides crucial evidence of the universe's origin, will fade into wavelengths so long that it becomes indistinguishable from the background noise of space. In that distant era, the clues to the universe's beginnings will vanish. And yet, the universe continues its slow journey. There is no abrupt ending, no final moment where everything suddenly stops. Instead, there is a gradual transition from brightness to dimness, from activity to stillness, from complexity to simplicity. It is a process that feels almost meditative. As you imagine this vast, quiet future, there is a certain calm in knowing that the universe does not rush. It unfolds patiently, over timescales so immense that even trillions of years feel like gentle steps in an endless journey. The fading of starlight is not just an ending, it is a transformation, a movement toward a quieter, darker state, where the echoes of what once was slowly dissolve into the fabric of space. And in this immense silence, time itself continues, steady, unbroken, and infinite. Chapter 2. When galaxies drift apart forever, as your awareness softens once more, we gently continue our journey, not just through space, but through time itself. Far beyond the fading of individual stars lies an even grander transformation, one that reshapes the very structure of the universe. Galaxies, those vast islands of stars, gas, and dark matter, are not fixed in place. They drift. Slowly, almost imperceptibly, they move through the expanding fabric of space. But this movement is not like ships crossing an ocean. It is more like the ocean itself stretching, carrying everything within it farther apart. The key to understanding this lies in a quiet but powerful discovery made in the 20th century by Edwin Hubble. He observed that distant galaxies appear to be moving away from us, and the farther they are, the faster they recede. This observation revealed that the universe is expanding uniformly in all directions. But here is where the story deepens. The expansion is not slowing down. Instead, it is accelerating. This acceleration is driven by something we cannot see directly, a mysterious component known as dark energy. It makes up about 68% of the total energy content of the universe, yet its nature remains one of the greatest unsolved mysteries in physics. You can imagine dark energy as a gentle but relentless force embedded within space itself, pushing everything apart. It does not act like gravity, which pulls objects together. Instead, it stretches space, increasing the distance between galaxies over time. At first, this expansion is subtle. Nearby galaxies, including our closest neighbors, remain bound together by gravity. For example, our galaxy, the Milky Way, is part of a small collection of galaxies known as the local group. Within this group, gravity is strong enough to hold galaxies together despite the expansion of the universe. In fact, the Milky Way is on a slow collision course with the Andromeda Galaxy. In about 4 to 5 billion years, these two galaxies will merge, forming a new, larger galaxy. It will be a slow, graceful interaction, stars passing by one another across vast distances, rarely colliding directly. But beyond the local group, things are very different. Galaxies that are not gravitationally bound to us are steadily drifting away. Over time, their recession speeds increase. Eventually, they move away so quickly that their light can no longer reach us. This creates a kind of cosmic horizon, a boundary beyond which events can never be observed. Here is a fascinating truth. This horizon is not fixed. It shrinks in terms of what we can see. As the universe expands faster and faster, more and more galaxies cross this boundary, effectively disappearing from our observable universe. Imagine standing in a vast field at night, watching distant lanterns slowly fade away, not because they are extinguished, but because they are carried beyond the reach of your vision. One by one, they vanish, leaving behind a darker and more isolated sky. This is the future of cosmic observation. Another subtle aspect of this process is how it affects the structure of the universe. Today, galaxies are arranged in vast filaments and clusters, forming what astronomers call the cosmic web. These structures are shaped by gravity, which pulls matter together over billions of years. But as dark energy dominates, the growth of these structures slows and eventually stops. Gravity can no longer overcome the accelerating expansion on large scales. The cosmic web freezes in place, and its large-scale evolution comes to an end. Within individual galaxy groups, however, gravity still plays a role. Over time, galaxies within the same group may merge, forming larger and more massive galaxies. These merged systems will contain the combined stars, gas, and dark matter of their predecessors. In the far future, the local group may become a single massive galaxy, sometimes referred to as Milkdromeda by astronomers. It will be surrounded by darkness, with no visible galaxies beyond its boundaries. This leads to a deeply intriguing realization. Future observers living in this merged galaxy may have no evidence that other galaxies ever existed. Without visible distant galaxies or detectable cosmic expansion, they might conclude that their galaxy is the entire universe. The evidence we rely on today, the redshift of galaxies, the cosmic microwave background, the large-scale structure of the cosmos, will gradually fade or become undetectable. This brings us to another quiet truth. The universe is not only changing physically, but also in terms of what can be known about it. As galaxies drift apart, the universe becomes more isolated. Each gravitationally bound system becomes like its own island universe, cut off from the rest. Communication or travel between these islands becomes impossible, not due to technological limits, but because of the fundamental nature of space itself. Even light, the fastest thing in existence, cannot bridge these ever-growing distances. Another fascinating detail is how this affects time perception on cosmic scales. While the expansion of the universe does not directly alter the passage of time locally, it changes the relationships between distant events. Signals take longer to travel, interactions become rarer, and the universe feels increasingly still. It is as if the cosmos is slowly stretching into silence. There is also a subtle beauty in how this process unfolds. It is not chaotic or violent. There are no sudden ruptures or dramatic endings. Instead, galaxies simply drift apart, following the gentle but persistent influence of dark energy. This gradual separation creates a universe that is smoother and more uniform over time. Differences in density even out, and large-scale structures become less pronounced. The universe approaches a state of maximum simplicity, vast, empty, and quiet. Yet, within each isolated galaxy, there may still be activity. Stars continue to evolve, remnants continue to interact, and local processes continue to unfold. But these events occur within increasingly confined regions, disconnected from the larger cosmic story. As you imagine this distant future, there is a sense of quiet inevitability. The universe does not resist its expansion. It does not slow or reverse. It continues outward, carrying galaxies farther apart with each passing moment. And with every expansion, the observable universe grows smaller. Not in size, but in what can be seen, known, and experienced. The night sky, once filled with countless galaxies, will gradually empty. What remains will be a single vast galaxy surrounded by darkness, a quiet island in an infinite sea, and beyond that darkness countless other islands, forever out of reach. As we continue drifting deeper into this quiet cosmic future, the separation between galaxies becomes more than just distance. It becomes a kind of permanent solitude. Not the kind we experience on Earth, but a vast, structural isolation built into the very fabric of space itself. In the earlier eras of the universe, galaxies were part of a shared story. Light from one could travel to another. Gravity could shape large-scale structures across immense regions. There was a sense of connection, a cosmic network where events in one region could, given enough time, influence another. But as dark energy continues its gentle, persistent push, that connection begins to dissolve. One of the most subtle yet profound consequences of this expansion is the creation of what physicists call an event horizon for the universe. Much like the boundary around a black hole beyond which nothing can return, the universe develops its own horizon, a limit beyond which events can never affect an observer. This doesn't mean those regions cease to exist. They continue evolving, forming stars, collapsing into black holes, and undergoing their own transformations. But their light, their signals, their entire history becomes forever inaccessible. Imagine an infinite library where entire sections slowly drift out of reach, not because they are destroyed, but because the corridors between them stretch endlessly. You know they are there, but you can never visit them again. This is the nature of cosmic isolation. Within our own region, the local group will continue to evolve as a self-contained system. Over billions of years, gravitational interactions will merge its galaxies into a single, massive structure. The Milky Way and the Andromeda Galaxy will combine, along with smaller satellite galaxies, forming a giant elliptical galaxy. This merged galaxy will be rich in stellar remnants, aging stars, and the quiet echoes of past collisions. But beyond it, there will be nothing visible. The rest of the universe will have slipped beyond the cosmic horizon. Another quiet truth emerges here. The expansion of the universe does not pull galaxies apart in the traditional sense. Instead, it stretches the space between them. This means that on smaller scales, within galaxies or galaxy clusters, gravity can still hold structures together. But on larger scales, expansion dominates. It is a delicate balance, one that shifts over time. As the universe ages, the dominance of dark energy becomes absolute. The rate at which galaxies recede increases exponentially. This leads to an almost surreal outcome. Distant galaxies don't just move away. They accelerate away so rapidly that even light emitted today will never reach us. This creates a kind of one-way boundary in time. There are events happening right now in distant galaxies that we will never see, no matter how long we wait. Another fascinating aspect of this future is how it changes the nature of observation itself. In our current era, Astronomy is built on the ability to observe distant objects, to measure their light, and to infer the structure and history of the universe. But in a far future isolated galaxy, this becomes impossible. Without visible external galaxies, there would be no evidence for cosmic expansion. Without the cosmic microwave background, there would be no direct clue to the Big Bang. The universe would appear static, eternal, and unchanging. This leads to a deeply intriguing idea. Knowledge of the universe's true nature may be limited not just by intelligence or technology, but by timing. We exist in a privileged era where the evidence is still visible. Future observers may not be so fortunate. In that sense, the universe slowly hides its own history. There is also a quiet transformation happening in the background radiation of the universe. Today, space is filled with the faint afterglow of the Big Bang, a nearly uniform microwave radiation that permeates all directions. But as the universe expands, this radiation stretches to longer and longer wavelengths. Eventually, it becomes so diluted and low energy that it is effectively undetectable. The universe grows colder, darker, and more silent. Another subtle effect of expansion is how it influences the energy of light itself. As photons travel through expanding space, their wavelengths stretch, and their energy decreases. This means that even the light that does reach us from distant objects becomes weaker over time. In the far future, the universe is not just darker because there are fewer stars. It is darker because the very light that remains carries less energy. This gradual dimming creates a universe that feels increasingly calm, almost suspended in a kind of cosmic stillness. Yet, within this stillness, time continues to flow. Inside the merged galaxy, stars continue their life cycles. Some will still shine for trillions of years. Others will evolve into white dwarfs, neutron stars, or black holes. These remnants may occasionally interact, forming binary systems or merging in rare events that release bursts of energy. But these events become increasingly rare. As distances grow and densities decrease, interactions become less frequent. The universe becomes not only darker, but quieter in terms of activity. The grand fireworks of galaxy collisions and star formation fade into isolated, sporadic events. There is also a fascinating interplay between gravity and expansion when it comes to extremely large structures. While galaxies themselves remain bound, larger superclusters may not. Over time, even these vast assemblies can be pulled apart by the accelerating expansion. This means that the universe's largest structures, once spanning hundreds of millions of light-years, will eventually dissolve into smaller, isolated systems. Another quiet truth is that the concept of distance itself becomes more abstract in this future. As space expands faster and faster, distances between unbound objects grow at an accelerating rate. Measuring or even conceptualizing these distances becomes increasingly difficult as they change continuously. It is as if the universe is stretching beyond the limits of comprehension. And yet, despite all this expansion, there is no central point from which everything moves away. Every observer, no matter where they are, sees other distant galaxies receding. The expansion is uniform, built into the fabric of space itself. This gives the universe a kind of symmetry, an elegant simplicity underlying its vast complexity. As your thoughts begin to settle into this slow, expanding vision, there is a certain calm in recognizing that the universe does not end abruptly. It does not collapse or shatter. Instead, it drifts gently, endlessly outward. Galaxies become islands. Islands become solitary. and the space between them grows into an ocean so vast that even light cannot cross it. In this quiet, ever-expanding cosmos, the connections that once defined the universe slowly fade, leaving behind a structure that is simpler, emptier, and profoundly still. And yet, it continues, always expanding, always unfolding. Chapter 3. The Quiet Death of Stars. Now, as the vast distances between galaxies continue to stretch into silence, we gently shift our focus inward, toward the stars themselves. These luminous anchors of the universe, which once filled the cosmos with warmth and brilliance, carry within them a quiet and inevitable ending. Stars may seem eternal when viewed from a human lifetime, but in truth, each one is living through a long and delicate balance. At their core, a star is a continuous struggle between two opposing forces: gravity pulling inward and nuclear fusion pushing outward. As long as this balance holds, the star shines steadily, releasing energy into the surrounding darkness. This balance is what allows stars like our own sun to glow for billions of years. But even the most stable systems cannot last forever. Deep within a star's core, hydrogen atoms are fused together to form helium. This process releases enormous amounts of energy, which travels outward and escapes as light and heat. It is this energy that supports the star against gravitational collapse. But hydrogen, like any fuel, is finite, and so begins the slow countdown. One of the most fundamental truths about stars is that their lifetimes are determined by their mass. Massive stars burn through their fuel quickly, shining intensely but briefly. Smaller stars burn slowly, conserving their energy over much longer timescales. For example, stars much larger than our Sun may live for only a few million years, a blink of an eye in cosmic terms. These stars burn hot and bright, often ending their lives in dramatic explosions known as supernovae. In contrast, smaller stars, especially red dwarfs, can live for trillions of years, quietly fusing hydrogen at a steady pace. This leads to a fascinating and calming realization. The smallest stars are the most enduring. They are the quiet keepers of light, outlasting their larger, more dramatic counterparts by unimaginable spans of time. As stars age, their internal structure begins to change. When a star exhausts the hydrogen in its core, fusion slows down, and gravity begins to take over. The core contracts, heating up in the process while the outer layers expand. For stars like our Sun, this transformation leads to the red giant phase. The star swells to many times its original size, its surface cooling and glowing with a reddish hue. In this phase, the star becomes both larger and more fragile, shedding its outer layers into space. These ejected layers form beautiful, glowing shells known as planetary nebulae, delicate structures that drift outward, illuminated by the fading core of the star. Though short-lived on cosmic timescales, they are among the most intricate and serene sights in the universe. At the center of this expanding shell remains the core, a dense, compact object known as a white dwarf. This remnant is incredibly small compared to the original star, yet it contains most of its mass. A teaspoon of white dwarf material would weigh tons on Earth. But a white dwarf does not generate new energy. It is no longer undergoing fusion. Instead, it slowly radiates away its remaining heat, cooling over billions and eventually trillions of years. Another quiet truth emerges here. Most stars in the universe will end their lives as white dwarfs. They will not explode or collapse dramatically, but simply fade, gradually cooling, becoming dimmer and dimmer until they are nearly invisible. For more massive stars, however, the ending is more intense. When such a star exhausts its nuclear fuel, its core collapses rapidly under gravity. This collapse can trigger a supernova explosion, briefly outshining entire galaxies. These explosions are not just dramatic, they are essential. They scatter heavy elements into space, seeding future generations of stars and planets. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all forged in the cores of stars and dispersed through such events. But even these powerful explosions are part of a larger, quiet cycle. After the explosion, the core that remains may become a neutron star, an incredibly dense object composed almost entirely of neutrons. These stars are so compact that a single teaspoon of their material would weigh billions of tons. They spin rapidly, sometimes emitting beams of radiation that sweep across space like cosmic lighthouses. And in the most extreme cases, the core collapses further, forming a black hole, a region of space where gravity is so strong that not even light can escape. Despite their dramatic origins, these remnants contribute to the overall quieting of the universe. They do not produce sustained light like living stars. Instead, they represent the aftermath, the fading echoes of once bright systems. As time stretches onward, the population of active, shining stars begins to decline. New stars form less frequently, while older stars continue to age and die. The balance shifts from creation to conclusion. This marks a gradual transition from a universe filled with vibrant, living stars to one dominated by remnants, white dwarfs, neutron stars, and black holes. And yet, this transition is not abrupt. It unfolds over trillions of years, allowing the universe to dim slowly, almost gently. There is no sudden darkness, no single moment when the lights go out. Instead, there is a long twilight, a period where light becomes rarer, softer, and more distant. As you imagine this slow fading, there is a certain calm in its predictability. Stars follow well-understood physical laws. Their births, lives, and deaths are governed by processes that, while complex, are deeply consistent. There is no chaos in their endings, only transformation. Even now, countless stars across the universe are at different stages of this journey. Some are just beginning, igniting their cores for the first time. Others are nearing their final moments, expanding into red giants or collapsing into dense remnants. This diversity creates a universe that is always changing, yet always following the same underlying rhythm. And as that rhythm continues, the number of active stars steadily decreases. The sky, once filled with brilliant points of light, begins to thin. Constellations lose their brightness. Galaxies grow dimmer, and the universe moves, step by step, toward a quieter state. But for now, the stars still shine. As the universe ages beyond billions and into trillions of years, the life cycles of stars begin to slow into something far more subtle, less dramatic, more quiet, almost meditative in nature. The brilliant explosions and energetic births that once defined galaxies become increasingly rare, replaced by long stretches of stillness. One of the most important shifts during this era is the near end of star formation. Earlier in cosmic history, galaxies were rich with cold hydrogen gas, the essential ingredient for new stars. These vast clouds would collapse under gravity, forming dense regions where nuclear fusion could ignite. But over time, that gas becomes scarce. Each generation of stars consumes a portion of it, and powerful events like supernovae can blow gas out of galaxies entirely. In the distant future, galaxies become gas-poor, meaning they lack the raw material needed to create new stars. This leads to a profound truth. There will come a time when no new stars are born at all. The universe transitions from a place of ongoing creation to one of gradual decline. The stars that exist will simply age, evolve, and fade, with no replacements to take their place. Another fascinating detail is how the remaining stars behave during this period. Red dwarfs, those small, efficient stars, become the dominant source of light. Unlike larger stars, they burn their fuel so slowly that they can shine for tens to even hundreds of trillions of years. These stars do not swell into red giants in the same dramatic way as larger stars. Instead, they evolve very gradually, becoming slightly hotter and brighter over time before eventually exhausting their fuel. Imagine a universe lit only by these faint, reddish points of light, scattered sparsely across immense distances. Their glow is soft, steady, and almost eternal from a human perspective. Yet even they have limits. As red dwarfs finally run out of hydrogen, they transition into what are known as white dwarfs, dense, cooling remnants. Over unimaginable timescales, these white dwarfs continue to radiate away their residual heat, becoming dimmer and colder. Eventually, they are expected to become black dwarfs, objects so cool that they emit virtually no detectable radiation. This stage has not yet occurred anywhere in the universe, simply because not enough time has passed. But it will, and when it does, the universe will be filled with these silent, dark remnants, ghosts of stars that once shone. There is also a subtle but important process that affects stellar remnants over long periods: gravitational interactions. Even in a quiet, aging galaxy, stars and remnants continue to influence one another through gravity. Occasionally, these interactions can lead to close encounters. A white dwarf might pass near another star, altering its trajectory. Two remnants might form a binary system, orbiting each other in a slow, intricate dance. In rare cases, these interactions can even lead to collisions. When two white dwarfs merge, they can sometimes trigger a delayed supernova, an unexpected burst of light in an otherwise dim universe. These events become exceedingly rare, but they serve as brief reminders that activity has not completely ceased. Still, such flashes of brightness are fleeting. The overall trend remains unchanged. The universe grows darker. Another quiet transformation involves neutron stars. These incredibly dense objects, formed from the collapsed cores of massive stars, continue to exist long after their progenitor stars are gone. Some neutron stars emit beams of radiation, appearing as pulsars when their beams sweep past observers. Over time, however, these pulsars lose energy. Their rotation slows, their emissions weaken, and eventually, they become nearly undetectable. They remain dense, compact, and silent. Black holes, too, play a role in this evolving landscape. While they do not emit light in the traditional sense, they can interact with surrounding matter. If a black hole captures gas or a passing star, it can produce bursts of radiation as that material is heated and consumed. But as the universe empties and matter becomes more dispersed, such interactions become less frequent. Black holes, like everything else, begin to experience long periods of inactivity. This leads to an important realization. The universe is not only losing light, but also losing events. Moments of change, of interaction, of transformation become increasingly rare. Time stretches between meaningful occurrences, creating a sense of stillness that deepens with each passing era. There is also an interesting shift in how energy is distributed. In earlier times, energy was concentrated in stars and galaxies, localized, intense sources of light and heat. But as these sources fade, energy becomes more evenly spread out across space. This process, often associated with the concept of entropy, leads the universe toward a state of maximum uniformity. Differences in temperature and energy diminish, and the cosmos approaches a kind of equilibrium. It is not an equilibrium of activity, but of quiet balance. Another subtle truth lies in the fate of stellar clusters. In the present universe, many stars exist in clusters, groups bound together by gravity. Over time, interactions within these clusters can cause stars to be ejected, gradually dispersing the cluster. In the far future, many clusters will dissolve entirely, their stars drifting independently through space. This further contributes to the isolation of individual objects within galaxies. The universe becomes not just darker, but more fragmented. As your thoughts settle into this vast, quiet future, it becomes clear that the death of stars is not a singular event, but a continuous process, one that unfolds across unimaginable spans of time. Each star follows its own path, its own timeline, its own quiet ending. And together, these countless individual endings weave a larger story, a slow, steady fading of light across the entire universe. There is no urgency in this process, no sudden collapse, only time stretching onward, carrying the cosmos gently from brightness into shadow. And in that shadow the remnants remain, silent, patient, waiting. Chapter 4. Black Holes and the Long Night. As the last generations of stars grow older and the universe settles into a quieter rhythm, a new kind of presence begins to dominate the cosmic landscape. These are not sources of light, but of gravity. Regions where matter has collapsed so completely that even light cannot escape. Black holes. They are often imagined as violent or destructive, but in the far future of the universe, they become something else entirely: patient, enduring, and strangely central to what remains. A black hole forms when a massive star reaches the end of its life and its core collapses under gravity. If the remaining mass is large enough, no known force can stop the collapse. The core compresses into an incredibly small region, creating what we call a singularity, surrounded by a boundary known as the event horizon. The event horizon is not a physical surface, but a point of no return. Anything that crosses it, matter, radiation, even information, is lost to the outside universe. In earlier cosmic eras, black holes are often surrounded by activity. Gas spirals into them, forming glowing accretion disks that shine brightly in X-rays. Collisions and mergers release bursts of energy that ripple across space as gravitational waves. But as the universe ages, these dramatic events become less frequent. There is less gas to feed black holes, fewer stars to fall into them, fewer interactions to disturb their quiet existence. And so, black holes begin to dominate not through action, but through persistence. One of the most fascinating truths about black holes is that they can grow. When two black holes merge, they form a larger one. When they consume matter, their mass increases. Over time, especially in dense regions like galactic centers, black holes can become incredibly massive. At the heart of most galaxies lies a supermassive black hole. In our own galaxy, the Sagittarius sits quietly at the center, containing millions of times the mass of the Sun. In the far future, as galaxies merge and evolve, these central black holes may also merge, forming even larger structures, cosmic anchors around which the remnants of galaxies slowly orbit. Yet, despite their immense power, black holes are not eternal in the way they were once thought to be. This leads us to one of the most subtle and profound discoveries in modern physics, associated with the work of Stephen Hawking. He proposed that black holes are not completely black. Due to quantum effects near the event horizon, they emit a faint form of radiation, now known as Hawking radiation. This radiation is incredibly weak, far too faint to detect from any known black hole today. But over extremely long periods of time, it has a significant consequence. Black holes slowly lose mass. They evaporate. This process is unimaginably slow for large black holes. A stellar mass black hole might take far longer than the current age of the universe to evaporate. A supermassive black hole could take trillions upon trillions of years, timescales so vast they are difficult to comprehend. But the key idea remains: black holes are not permanent. Even the most massive structures in the universe are subject to change. Before we reach that distant future, however, black holes will play a central role in shaping what remains of galaxies. As stars evolve and die, their remnants, white dwarfs, neutron stars, and smaller black holes, continue to move through space. Occasionally, these objects will pass close to a black hole. When they do, gravity takes over. Some may be captured into orbit, forming complex systems. Others may be torn apart by tidal forces in a process known as spaghettification, where the difference in gravitational pull across an object stretches it into long, thin streams. These streams of matter can form temporary accretion disks, briefly lighting up the black hole's surroundings before the material is consumed. But such events become rarer with time. As the universe expands and matter becomes more dispersed, black holes spend longer periods in isolation. They sit in the centers of galaxies that are themselves growing quieter, surrounded by fewer and fewer active stars. This leads to a fascinating shift in the balance of the universe. In earlier times, stars were the primary contributors to the universe's energy output. Their light and heat dominated the cosmic environment. But as stars fade, black holes, despite their darkness, become the most significant structures in terms of mass and gravitational influence. The universe transitions from being star-dominated to black hole-dominated. Another quiet truth lies in how black holes influence their surroundings over long periods. Their gravitational pull can alter the orbits of nearby stars and remnants, gradually reshaping the structure of galaxies. In some cases, stars may be ejected from galaxies entirely due to complex gravitational interactions involving black holes. These stars become isolated travelers, drifting through intergalactic space. Over immense timescales, even galaxies themselves can become less stable. Interactions between objects, combined with the influence of central black holes, can lead to a gradual redistribution of matter. The universe becomes more diffuse, more spread out, more still. And yet, black holes remain. They do not shine. They do not burn. They simply exist, holding on to mass, shaping their surroundings through gravity alone. There is something almost meditative about their presence. In a universe that is slowly losing light and activity, black holes represent continuity. They are long-lived, stable, and deeply connected to the history of everything that came before. Every black hole carries within it the memory of the star that formed it, or the matter it has consumed. Though we cannot see inside them, they are, in a sense, archives of cosmic history. As your thoughts drift through this quiet era, imagine a universe where the brightest lights have faded, where galaxies are isolated, and where black holes sit at the centers of vast, silent systems. There are no fireworks, no bursts of creation, only the slow movement of remnants and the steady presence of gravity. The long night has begun, As the universe continues its slow descent into darkness, black holes remain among the last dominant structures, quiet, massive, and enduring. But even in this era of stillness, subtle processes continue to unfold around them, shaping the final chapters of cosmic evolution in ways that are both gentle and profound. One of the most fascinating aspects of black holes in this distant future is how isolated they become. In earlier epochs, galaxies were rich with stars, gas, and dynamic interactions. Black holes often had access to surrounding matter, occasionally feeding and producing bursts of radiation. But as time stretches into trillions upon trillions of years, these opportunities become increasingly rare. The universe grows emptier, stars fade, gas dissipates, encounters become uncommon, and so, black holes enter long periods of quiet inactivity, drifting in the centers of galaxies that themselves have become sparse collections of aging remnants. Yet even in isolation, gravity continues its quiet work. Within a galaxy, stellar remnants, white dwarfs, neutron stars, and smaller black holes continue to move in slow orbits. Over immense timescales, their paths may intersect. Occasionally, one of these objects wanders too close to a larger black hole. When this happens, the outcome depends on the nature of the encounter. Some objects are gently captured, entering into wide, stable orbits. Others spiral inward over time, gradually losing energy until they are consumed. In rare cases, a compact object like a neutron star may merge directly with a black hole, releasing a faint ripple through space-time, gravitational waves traveling silently across the cosmos. These events, while extraordinary, become increasingly infrequent. Time between such interactions grows longer, and longer until entire eras pass without significant change. Another quiet truth is that black holes themselves can form binary systems. Two black holes orbiting each other create a slow, spiraling dance, gradually drawing closer as they emit gravitational waves. This process can take billions or even trillions of years, depending on their separation. Eventually, they merge. The result is a slightly larger black hole, accompanied by a brief but powerful release of gravitational energy. In earlier cosmic times, such events were more common and detectable. In the far future, they become rare echoes, subtle disturbances in an otherwise silent universe. But even as black holes merge and grow, a deeper, almost paradoxical process is unfolding. They are also slowly disappearing. This is the quiet influence of Hawking radiation, first proposed by Stephen Hawking. According to this idea, black holes are not perfectly stable. Quantum effects near the event horizon cause them to emit a tiny amount of radiation, leading to a gradual loss of mass. At first, this loss is negligible. A massive black hole barely changes over billions or trillions of years. Its evaporation is so slow that it seems eternal from any practical perspective. But given enough time, even the largest black holes begin to shrink. This introduces one of the most astonishing timescales in all of physics. A supermassive black hole may take on the order of 10 superscript 1 years or more to fully evaporate, a number so large that it dwarfs the current age of the universe by an unimaginable margin. To put it gently, if the entire history of the universe so far were compressed into a single second, the evaporation of such a black hole would take longer than the lifetime of countless universes stacked one after another. And yet, it will happen. As black holes lose mass, their temperature paradoxically increases. Smaller black holes emit more radiation than larger ones. This means that as a black hole shrinks, the rate of its evaporation accelerates. In its final stages, a black hole may release a brief burst of energy before disappearing completely. This is not an explosion in the traditional sense, but a final release, a quiet ending to an incredibly long existence. Imagine a universe where the last remaining sources of structure are these slowly evaporating black holes. Each one, over incomprehensible spans of time, fades away, leaving behind nothing but the faintest traces of radiation. Another subtle transformation during this era involves the distribution of matter itself. As black holes interact with surrounding objects, they can eject some material through complex gravitational interactions. Over time, this contributes to an even more diffuse universe, where matter is spread thinly across vast distances. The cosmos becomes increasingly uniform. Differences in density diminish, structures dissolve, and the universe approaches a state of near-complete simplicity. There is also an intriguing question about information. What happens to the information contained within objects that fall into black holes? This is known as the black hole information paradox, a topic that has been explored deeply in theoretical physics. While the full answer remains uncertain, many theories suggest that information is not truly lost, but somehow encoded in subtle ways, possibly in the radiation emitted as the black hole evaporates. If this is true, then black holes are not just endpoints but transformers, converting matter and information into new forms that are spread across the universe. Even in their quiet fading, they participate in the ongoing story of the cosmos. As your thoughts drift through this immense future, there is a sense of profound stillness. The universe is no longer a place of bright stars and dynamic galaxies. It is a vast, dark expanse, punctuated only by the slow, patient presence of black holes. And even they are temporary. The long night is not just about darkness, it is about duration. It is about processes that unfold over timescales so vast that they transcend ordinary understanding. Yet, there is a certain peace in this. The universe does not rush toward its end. It unfolds gently, step by step, allowing every structure, every object, every remnant to follow its natural course. Black holes, once feared as devourers of light, become quiet markers of time, measuring the slow passage of the universe toward an even deeper silence. And as they fade, the night grows longer. Chapter 5. The cooling of the cosmos. As the long night deepens and the last active sources of light become rare, the universe begins to undergo another transformation, one that is quieter than fading starlight and slower than the drifting of galaxies. It begins to cool, not suddenly, not dramatically, but steadily, almost imperceptibly, like a warm surface left untouched in an endless night. Temperature in the universe is tied to motion and energy. In the early cosmos, everything was dense, hot, and energetic. Particles moved rapidly, radiation filled space, and interactions were constant. But as the universe expands, that energy spreads out. Distances grow, interactions decrease, motion slows, and so, the overall temperature drops. One of the most important remnants of the universe's hot beginning is the cosmic microwave background. This faint radiation fills all of space, a quiet echo of the early universe when everything was much hotter and denser. Today, this background radiation has a temperature of about 2.7 Kelvin, just above absolute zero. It is already incredibly cold. Yet, as the universe continues to expand, this temperature will keep decreasing. The wavelengths of this radiation stretch further and further, reducing its energy. Over time, It fades into something even more subtle, eventually becoming almost undetectable. This leads to a profound realization. The universe is not just losing light, it is losing warmth. Another quiet truth lies in how isolated systems cool over time. Consider a star remnant like a white dwarf. Without ongoing fusion, it has no internal source of energy. It simply radiates away its remaining heat, cooling gradually. Given enough time, trillions upon trillions of years, it will reach temperatures so low that it becomes effectively invisible, a black dwarf, indistinguishable from the surrounding darkness. Now imagine this happening everywhere. Not just to one star, but to every star, every remnant, every object that once held heat. The entire universe slowly approaches thermal equilibrium, a state where temperature differences disappear and everything settles into a uniform, cold condition. This process is closely related to the concept of entropy. In simple terms, entropy describes how energy becomes more evenly distributed over time. Systems naturally evolve toward states of higher entropy, where energy is spread out and less available to do work. In the early universe, energy was concentrated. Stars burned brightly, galaxies formed, and structures evolved. But as entropy increases, that energy becomes diluted. Differences in temperature and density smooth out, leading to a more uniform and less dynamic cosmos. This is sometimes referred to as the heat death of the universe. Not a violent end, but a gradual fading into equilibrium. It is important to understand that this death is not the destruction of matter, but the loss of usable energy. The universe still exists, but it becomes a place where no significant processes can occur. No stars form, no light shines, no warmth remains. Just a vast, cold expanse where everything is evenly spread and slowly drifting. Another subtle effect of cooling involves the behavior of particles themselves. At higher temperatures, particles move quickly and interact frequently. But as temperatures drop, motion slows and interactions become rare. Atoms may still exist, but they drift through space with minimal interaction. Collisions become infrequent. Chemical reactions, once common in the warmer, denser universe, become nearly impossible. The universe becomes chemically quiet. Even radiation, which once carried energy across vast distances, becomes less effective as a source of interaction. Photons stretch to longer wavelengths, losing energy, becoming less capable of influencing matter. Light itself becomes a faint whisper. There is also an interesting transformation in how time is experienced in such a universe. While time itself does not slow, the lack of events gives the impression of stillness. With fewer interactions, fewer changes, and fewer sources of energy, the universe feels almost frozen in place. Moments pass, but little happens. Another quiet truth emerges when we consider the scale of this cooling process. It does not happen uniformly everywhere at once. Local variations persist for long periods. Some regions may remain slightly warmer due to residual energy or rare interactions. But over immense timescales, these differences fade. The universe smooths out. It becomes more uniform, more balanced, more still. There is also a gentle beauty in this transition. The universe is not collapsing or tearing itself apart. It is simply relaxing, moving toward a state of minimum energy, where everything is calm and evenly distributed. It is a kind of cosmic rest. As you imagine this future, picture a universe where temperature differences no longer drive change, where there are no hot stars or glowing nebulae, no bursts of energy or sudden transformations, only a quiet, uniform cold. And yet, even in this stillness, Time continues. Particles drift. Radiation stretches. Black holes slowly evaporate. The universe does not stop. It simply becomes quieter. Another fascinating detail lies in how this cooling affects the concept of structure. In earlier times, differences in temperature and density allowed structures to form: stars, galaxies, clusters. But as these differences fade, the ability to form new structures disappears. The universe becomes structurally simple. What remains are remnants of earlier complexity, objects that formed long ago and are now slowly fading. This gives the universe a kind of memory. Even as it cools and simplifies, it carries traces of its past. Faint, fading imprints of a time when it was vibrant and full of activity. As your thoughts settle into this calm, cooling vision, there is a sense of inevitability, but also of peace. The universe is not ending in chaos. It is settling into stillness, a slow, gentle cooling that continues, and continues, and continues. As the universe continues its slow drift toward lower and lower temperatures, the idea of cold itself begins to take on a deeper meaning. It is no longer just the absence of warmth, but the absence of activity, of change, of interaction. The cooling of the cosmos is not something that happens in a single moment. It unfolds across unimaginable spans of time, quietly reshaping the nature of everything that exists. One of the most subtle truths is that absolute zero, the theoretical point where all motion stops, may never actually be reached. Instead, the universe approaches it asymptotically, getting closer and closer, but never quite arriving. There is always a tiny amount of residual motion, a faint trace of energy that persists. Even in the coldest future, something still moves. Yet that movement becomes so minimal that, for all practical purposes, the universe feels completely still. Another fascinating aspect of this era is how it changes the behavior of radiation. In earlier times, radiation played a major role in transferring energy. Stars emitted light, galaxies glowed, and the cosmic background provided a faint but measurable energy field. But as expansion continues, all radiation stretches. Its wavelength grows longer, its energy weaker. Over time, even the most energetic photons are reduced to extremely low energy forms. Eventually, radiation becomes so diluted that it has almost no effect on matter at all. Light, once the defining feature of the universe, becomes nearly irrelevant. This leads to a profound shift. The universe transitions from being radiation-influenced to matter-dominated in a quiet, passive sense. But even matter itself is no longer active. Without significant temperature differences or energy gradients, matter simply exists, drifting through space without interaction. Another quiet truth lies in how objects exchange heat. In our current universe, heat flows from warmer objects to cooler ones, driving countless processes. But in a nearly uniform, ultra-cold universe, there are no meaningful temperature differences. Heat has nowhere to flow. Everything is already as cold as everything else. This creates a state where thermodynamic processes effectively cease. No engines can run, no reactions can occur, no structures can evolve further. The universe reaches a kind of thermal stillness. And yet, time continues. There is also an interesting consequence for any remaining structures, such as planets or stellar remnants. Without nearby stars or external heat sources, these objects cool to match the background temperature of the universe. Planets become frozen, dark spheres. White dwarfs fade into black dwarfs. Neutron stars lose their residual heat. Even black holes, though governed by different physics, contribute to this cooling trend through their slow evaporation. Another subtle effect of extreme cooling involves quantum behavior. At very low temperatures, quantum effects can become more noticeable in certain systems. However, in the vast emptiness of space, where particles are sparse and interactions are rare, even these effects remain largely isolated and insignificant on a cosmic scale. The universe becomes not only cold, but quiet at every level. There is also a shift in how we might think about timescales in such an environment. In a universe filled with activity, time is marked by events: stars forming, galaxies colliding, particles interacting. But in a universe approaching thermal equilibrium, events become so rare that time loses its usual meaning. Millions, billions, even trillions of years may pass with almost no noticeable change. Time stretches into something almost abstract. Another fascinating truth is that the cooling of the universe is directly tied to its expansion. As space grows, energy spreads out. This relationship means that as long as the universe continues to expand, cooling will continue as well. If expansion never stops, neither does the cooling. This creates a future that is not defined by a single endpoint, but by an ongoing approach towards stillness. A journey that never quite finishes, but gets closer with each passing moment. There is also a gentle symmetry in this process. The universe began in an extremely hot, dense state, where everything was compressed and energetic. Over time, it expands, cools, and becomes more diffuse. From heat to cold, from density to emptiness, from activity to stillness. They are like faint ripples in an endless ocean. As your thoughts drift through this nearly frozen universe, there is a sense of profound calm. Nothing rushes. Nothing demands attention. Everything simply exists in a state of quiet balance. The concept of change becomes almost irrelevant. And yet, the universe is not truly static. Expansion continues. Cooling continues. Subtle processes unfold over unimaginable timescales. The story does not end. It simply becomes quieter and quieter. Another intriguing idea is that in such a cold, uniform universe, the distinction between different regions becomes less meaningful. Without significant variations in temperature or density, one part of the universe becomes nearly indistinguishable from another. It is a kind of cosmic uniformity where uniqueness fades. But within this uniformity lies a deep simplicity. The universe, once complex and full of structure, has evolved into a state that is minimal and balanced. It has shed its extremes, its contrasts, its bursts of energy, and settled into something calm and enduring. There is a quiet beauty in that. Not the beauty of bright stars or colorful nebulae, but the beauty of stillness, of completeness, of a journey that has gradually reached its most peaceful state. And as everything cools further, approaching that unreachable boundary of absolute zero, the universe continues its endless, silent expansion. No longer vibrant, no longer bright, but still present. Chapter 6. Proton Decay and the Disappearance of Matter. As the universe settles into its cold, quiet state, an even deeper transformation begins to unfold, one that reaches into the very structure of matter itself. Until now, stars have faded, galaxies have drifted apart, and energy has thinned across space. But matter, the solid foundation of everything we know, has remained. Or at least it seems that way. For most of human understanding, protons, the positively charged particles at the heart of every atom, were considered stable. Eternal, unchanging, fundamental. Every object you have ever touched, Every star that has ever shone, every planet that has ever formed, all built upon protons. But modern physics introduces a quiet and unsettling possibility. Protons may not last forever. This idea emerges from certain theories in particle physics, particularly those that attempt to unify the fundamental forces of nature. These theories suggest that, over incredibly long timescales, protons might decay into lighter subatomic particles. This process is known as proton decay. It has never been observed, not once, and yet experiments have placed lower limits on how long a proton might last, at least 10^3 years and possibly far longer. To put that into perspective, this is vastly greater than the current age of the universe. If proton decay does occur, it is one of the slowest processes imaginable. So slow that it feels almost indistinguishable from permanence. But over the immense stretches of time we are now exploring, trillions upon trillions of years, even the rarest processes begin to matter. Imagine a single proton, sitting quietly within an atom, unchanged for longer than stars have existed. Now imagine that, after an unfathomable span of time, it suddenly transforms, decaying into lighter particles such as positrons and neutral pions. This transformation releases a tiny amount of energy, and the atom ceases to exist. Multiply this process across the entire universe, and a remarkable picture begins to form. Matter itself slowly dissolves, not through destruction, not through collision, but through quiet transformation at the most fundamental level. Another subtle truth is that not all matter would decay at the same time. Proton decay, if it occurs, would be a random process. Some protons might last longer than others. Some atoms might persist far longer than their neighbors. But given enough time, the trend becomes clear. Fewer and fewer stable particles remain. Objects that once seemed permanent, rocks, planets, even stellar remnants, begin to lose their structure. Atoms break apart. Molecules vanish. The distinction between solid and empty fades. The universe transitions from a place filled with matter to one where matter itself becomes rare. There is something deeply profound about this idea. Up to this point, the universe has been evolving in terms of energy and structure. But now, the very building blocks of existence are changing. It is not just the end of stars or galaxies. It is the slow disappearance of substance. Another fascinating aspect of proton decay is how it affects larger structures. Consider a white dwarf, a dense stellar remnant composed mostly of carbon and oxygen nuclei. These nuclei are made of protons and neutrons. If protons decay, then over time, the entire structure of the white dwarf begins to unravel. Atoms lose their identity. The dense matter gradually transforms into lighter particles and radiation. The white dwarf, once a stable remnant, slowly dissolves into a cloud of low-energy particles. This process applies to all forms of matter. Neutron stars, though composed mostly of neutrons, are not immune. Neutrons themselves can decay under certain conditions, and the presence of protons within these stars means that they too are subject to this long-term transformation. Even planets, cold, dark, and long abandoned by light, are not permanent. Their atoms, once locked in solid structures, eventually break down. Everything becomes temporary. Another quiet truth lies in how this process contributes to the overall simplicity of the universe. As complex structures dissolve, what remains are simpler particles, electrons, positrons, neutrinos, and photons. The rich complexity of atoms and molecules gives way to a more basic, more uniform state. The universe becomes less structured, less differentiated. more minimal. There is also a fascinating connection between proton decay and the concept of conservation laws in physics. In many current theories, certain quantities, like baryon number, are conserved, meaning they remain constant in interactions. But in theories that allow proton decay, this conservation is not absolute. Over long timescales, these quantities can change, leading to the gradual transformation of matter into radiation and lighter particles. This challenges our intuitive sense of permanence. What we think of as stable may only be stable within a certain window of time. Beyond that window, everything changes. Another subtle effect of proton decay is how it contributes to the overall energy balance of the universe. Each decay releases a small amount of energy, but this energy is quickly spread out across space, becoming part of the low-energy background. It does not create new structures or restore activity. It simply adds to the quiet, diffuse energy of the cosmos. As you imagine this process unfolding, there is a sense of incredible patience in the universe. Nothing happens quickly. There are no sudden transformations. Instead, there is a slow, steady progression toward simplicity. Atoms become particles. Particles drift. Energy spreads. And the universe continues its journey toward stillness. There is also an almost poetic symmetry in this idea. The universe began with simple particles that combined to form atoms, stars, and galaxies. Now, over immense timescales, those structures dissolve back into simpler components. From simplicity to complexity, and back again. But this return is not a reversal. It is a continuation, a quiet unfolding of the same underlying laws that have guided the universe from the beginning. As your thoughts settle into this deep, subtle transformation, consider how different this ending is from what we might expect. There is no explosion, no collapse, no dramatic finale. As the quiet process of proton decay continues across unimaginable spans of time, the universe begins to lose not just structure, but identity. The familiar distinctions between solid and empty, between object and space, gradually dissolve into something far more uniform. At first, this transformation is subtle. A few atoms here and there quietly decay, their components drifting away as lighter particles. No sudden collapse, no visible disruption. Just a slow, steady thinning of matter across the cosmos. But over trillions upon trillions of years, the cumulative effect becomes profound. Objects that once seemed permanent, asteroids, planets, even the dense remnants of stars, begin to lose mass. Their internal structures weaken as the atoms that hold them together gradually vanish. What was once solid becomes porous, then diffuse, and eventually almost indistinguishable from the surrounding space. Imagine a vast, dark planet, long abandoned by light, slowly dissolving from within, not crumbling, not breaking apart, but gently fading, as if its substance is being quietly rewritten at the smallest possible scale. Another fascinating truth is that as matter decays, the universe becomes increasingly dominated by radiation and lightweight particles. Electrons, positrons, neutrinos, and photons drift freely through space, no longer bound into complex structures. This marks a transition from a matter-dominated universe to one where energy exists primarily in these simple, unbound forms. And yet, even this energy is faint. Each decay event releases only a small amount, and as space continues to expand, that energy spreads out, becoming thinner and less concentrated. The universe does not grow brighter from these processes. It remains dim, cold, and quiet. There is also an interesting shift in how we might think about objects. In earlier eras, objects were defined by their structure, atoms forming molecules, molecules forming matter. But as proton decay progresses, these structures no longer persist. Instead, what remains are fleeting groupings of particles, drifting through space without cohesion. The concept of a stable object begins to disappear. Another subtle effect involves the remnants of previously complex systems. For example, a white dwarf that has been cooling for trillions of years may already be a black dwarf, cold, dark, and inactive. As proton decay continues, even this dense remnant begins to lose its integrity. Atoms within it decay. The lattice of matter weakens. Gradually, the black dwarf transforms into a diffuse cloud of particles, spreading outward into space. The same applies to neutron stars. Though incredibly dense, they are not immune to the slow processes that govern the universe at these timescales. Over immense periods, even their tightly packed matter begins to break down. Everything softens. Everything disperses. Another quiet truth lies in the randomness of proton decay. Because it is a probabilistic process, there is no uniform timeline for when specific objects will disappear. Some regions of space may retain remnants of matter longer than others. But given enough time, the outcome is the same everywhere. Matter becomes rare, then rarer still, until it is almost gone. There is also a profound implication for the concept of permanence. In our everyday experience, matter feels stable. Mountains endure, planets persist, and even stars last for billions of years. But on these vast cosmic timescales, permanence reveals itself as an illusion. Everything changes. Everything fades. Even the building blocks of existence. Another fascinating detail is how this process interacts with black holes. Black holes, which have been slowly evaporating through Hawking radiation, may outlast most forms of matter. For long periods, they remain as some of the last structured entities in the universe. But as proton decay reduces the amount of surrounding matter, black holes have less to interact with. They become increasingly isolated, surrounded by vast expanses of near-empty space. Eventually, even they will fade. This creates a universe where both matter and structure are in decline simultaneously. Black holes shrink, matter dissolves, and what remains is a thin, diffuse mixture of particles and radiation. Another subtle transformation involves the balance between particles and antiparticles. Some decay processes produce positrons, the antimatter counterparts of electrons. When these particles encounter electrons, they annihilate, producing photons. These annihilation events release energy, but again, in such a vast and expanding universe, the energy quickly dissipates. They are brief flashes in an otherwise quiet cosmos. There is also a gentle shift in how the universe looks, though there are no observers in the traditional sense. If one could perceive this era, it would appear almost empty, an immense expanse with only the faintest traces of particles drifting through it. No stars, no galaxies, no solid objects, only motion at the smallest scales. And even that motion is minimal. Another quiet truth is that the disappearance of matter simplifies the universe in a profound way. Complexity, which once arose from the interactions of countless particles, fades as those particles themselves become scarce. The universe approaches a state of minimal structure, where the distinction between different regions becomes almost meaningless. It is a return to simplicity, but not the same simplicity as the early universe. This is not a hot, dense beginning, but a cold, diffuse ending. A quiet symmetry. As your thoughts drift through this nearly matterless cosmos, there is a sense of deep stillness. The universe has not ended, it has transformed. From a place filled with light and structure, to one defined by absence and simplicity. And yet, even here, time continues. Particles drift. Radiation stretches. Black holes slowly evaporate in the distance. The story does not stop. It simply becomes softer, quieter, more subtle with every passing moment. And in this vast, fading expanse, matter itself becomes a memory, carried only in the faintest traces of what once was. Chapter 7. The Era of Dark Remnants. As matter itself begins to thin and the last traces of structure quietly dissolve, the universe enters a phase unlike anything before it. An era defined not by what is present, but by what remains. This is the age of remnants. Not living stars, not active galaxies, but the quiet leftovers of everything that once was. White dwarfs that have cooled into darkness. Neutron stars that no longer pulse. Black holes lingering in isolation. Sparse particles drifting across an ever-expanding void. The universe has not ended. It has simply become minimal. One of the most striking truths of this era is that nearly all familiar forms of matter have already disappeared or transformed. Proton decay, if it occurs, has reduced most atomic structures into simpler particles. Complex systems, planets, stars, even stellar corpses, have lost their identity. What remains are the densest and most stable remnants, and even they are slowly changing. Black holes, in particular, take on a central role during this time. With most matter gone and star formation long ceased, they become the dominant gravitational structures in the universe. Though invisible, their presence defines what little structure still exists. They are the final anchors of what were once galaxies. But even among black holes, there is a quiet evolution taking place. Larger black holes may have formed through countless mergers over earlier eras, growing to immense sizes. Smaller ones may still drift through space, remnants of ancient stars. Yet, regardless of size, they all share the same fate: slow evaporation. This means that even the most dominant objects in this era are temporary. Another fascinating detail is how empty space truly becomes. In earlier cosmic times, even the vast voids between galaxies contained traces of gas, radiation, and dark matter. But now, with matter decaying and radiation stretching, these voids become even emptier. Distances between particles grow enormous. Encounters become almost non-existent. The universe becomes a place where isolation is the norm, not the exception. There is also a subtle transformation in how gravity shapes what remains. With so little matter left, gravitational interactions become extremely rare. Objects that are still bound, such as remnants within a former galaxy, may continue to orbit each other, but these systems gradually lose members over time. Through slow gravitational interactions, objects can be ejected, drifting away into the void. Over immense timescales, even these small systems begin to dissolve. Everything spreads out. Everything drifts apart. Another quiet truth lies in the persistence of motion. Even in this nearly empty universe, particles and remnants continue to move. Their paths may be simple and uninterrupted, but motion never fully ceases. A lone particle may travel for billions or trillions of years without encountering anything else. A black hole may drift through space, surrounded by nothing but darkness, its presence detectable only through its gravitational influence. This creates a universe that is not static, but incredibly sparse in its activity. There is also an interesting shift in scale. In earlier times, Structures like galaxies and clusters define the large-scale organization of the universe. But in this era, those structures no longer exist in any meaningful sense. Instead, the universe is defined by individual remnants, isolated points of mass or energy, separated by vast distances. The concept of a system becomes less relevant. Everything is alone. Another subtle aspect of this era is how it reflects the history of the universe. Every remnant carries with it a story, a past shaped by billions or trillions of years of evolution. A black hole formed from a collapsing star, a neutron star born in a supernova, a white dwarf that once shone brightly. Even as these objects fade or evaporate, they are echoes of what came before. The universe, in this sense, becomes a collection of memories, faint, distant, and slowly disappearing. There is also a profound simplicity that emerges. With complex structures gone, the universe is governed by only the most fundamental interactions. Gravity, quantum processes, and the slow expansion of space continue to shape what little remains. It is a return to basics, a universe stripped down to its core principles. Another fascinating truth is that time, in this era, becomes almost immeasurable in the usual sense. Without frequent events or changes, there are few markers to distinguish one moment from another. Time flows, but nothing significant happens to mark its passage. It is a kind of timelessness, not because time has stopped, but because change has become so rare. There is also a gentle beauty in this minimalism. The universe is no longer vibrant or dynamic, but it is calm, consistent, and deeply quiet. It has shed its complexity and settled into a state that is simple and enduring. Not dramatic, not chaotic, just still. As your thoughts drift through this era of dark remnants, imagine a universe where the last traces of structure are scattered across an immense, empty expanse, where black holes drift slowly, where particles move without interaction, and where the memory of stars exists only in the remnants they left behind. There is no light, no warmth, no creation, only the quiet continuation of existence. And even this, as we will see, is not permanent. In this vast and quiet epoch, where almost everything familiar has already faded, what remains continues to drift, slowly, patiently, almost without purpose. The universe has entered a stage where activity is no longer the norm, but a rare and fleeting exception. And yet, even here, subtle processes continue to unfold. One of the most fascinating truths about this era is that motion still persists, even in extreme emptiness. A lone electron, a neutrino, or a photon can travel unimaginable distances without ever encountering another particle. Space has expanded so much, and matter has become so sparse, that interactions are nearly non-existent. This creates a universe where particles behave almost like independent travelers, each following its own path through a silent, infinite expanse. But occasionally, very rarely, two particles may meet. When they do, something small but meaningful can occur. Annihilation between a particle and its antiparticle may produce a pair of photons. A weak interaction might slightly alter a particle's trajectory. These events are incredibly infrequent, separated by vast stretches of time. Yet they remind us that the universe is never completely still. Another quiet truth lies in the gradual disappearance of even the densest remnants. Black holes, which once seemed like the final enduring structures, continue their slow evaporation through Hawking radiation. Over timescales so vast they defy imagination, they lose mass, shrink, and eventually vanish. At first, this process is almost imperceptible. But as a black hole becomes smaller, its rate of evaporation increases. Near the end of its existence, it releases a final burst of radiation, a brief, subtle flare in an otherwise dark universe. Then it is gone. With the disappearance of black holes, the last significant concentrations of mass fade away. What remains is a universe composed almost entirely of low-energy particles and radiation, spread thinly across an ever-expanding space. This marks a profound transition. The universe is no longer a place of objects. It becomes a place of fields and particles. Another fascinating detail is how the concept of location begins to lose meaning. In earlier times, objects were grouped into structures: stars within galaxies, galaxies within clusters. But now, with everything dispersed, there are no clear boundaries or groupings. A particle's location is simply a point in an immense, uniform expanse. There are no neighborhoods, no centers, no edges, just space, stretching endlessly in all directions. There is also a subtle shift in how energy behaves. With no dense structures to contain or interact with it, energy becomes increasingly diffuse. Photons continue to stretch as the universe expands, losing energy and becoming longer in wavelength. Eventually, even these photons carry so little energy that they have almost no measurable effect on anything else. They exist, but barely. Another quiet truth is that the universe at this stage is incredibly stable. Without significant forces or interactions to drive change, it remains in a state that is almost unchanging. The laws of physics still apply, but there is very little for them to act upon. It is a kind of cosmic equilibrium, not a dynamic balance but a static one. There is also an interesting philosophical aspect to this era. If there were a way to observe it, it might appear as though nothing is happening. The universe would seem empty, silent, and unchanging. And yet, beneath that stillness, processes continue. Slow, subtle, and almost imperceptible. Time flows, particles drift, expansion continues. Another fascinating detail is how rare fluctuations might still occur. Even in a nearly empty universe, quantum mechanics allows for tiny, spontaneous variations in energy. These fluctuations are incredibly small and fleeting, but they represent the last traces of unpredictability in an otherwise uniform cosmos. They are like faint ripples on an endless, calm ocean. There is also a sense in which the universe has reached its simplest possible form. Complexity, which once defined everything from atoms to galaxies, has been reduced to its most basic elements. No chemistry, no structure, no hierarchy, just particles and fields. And yet, even in this simplicity, the universe continues to exist. Another quiet truth is that this era lasts for an incomprehensibly long time. Once the last black holes have evaporated and matter has decayed, there are no major processes left to drive further change. The universe remains in this state for durations that far exceed everything that came before. It is not an ending in the traditional sense. It is a continuation without events. As your thoughts settle into this profound stillness, there is a certain calm in recognizing that the universe does not collapse or disappear. It does not reach a final moment where everything stops. Instead, it becomes quieter, simpler, more uniform. A vast expanse where almost nothing happens. And yet, something still remains. Existence itself. Even without stars, without galaxies, without matter as we know it, the universe persists. Space continues to expand. Time continues to flow. the underlying fabric of reality remains intact. There is a quiet resilience in that, a sense that even when everything we recognize has faded, the universe itself continues, steady and unbroken. And in that endless, silent expanse, the story does not end. It simply becomes almost impossible to notice. Chapter 8. The final evaporation of black holes. In the immense quiet that follows the era of dark remnants, one final process continues to unfold, slow, subtle, and almost impossible to perceive unless you stretch your imagination across incomprehensible spans of time. Black holes, the last great structures of the universe, are still here, but they are changing. For most of cosmic history, black holes were seen as endpoints, regions where matter and light disappeared, never to return. They seemed permanent, unchanging, immune to the passage of time. Yet, as we now understand, even these silent giants are not beyond the reach of the universe's quiet transformations. They fade. The idea begins with a subtle quantum effect near the edge of a black hole, a region known as the event horizon. Space at this boundary is not empty in the classical sense. Instead, it is filled with tiny fluctuations, pairs of particles that briefly appear and disappear. Under normal conditions, these pairs annihilate almost instantly, leaving no trace. But near a black hole, something unusual can happen. One particle falls inward, crossing the event horizon, while the other escapes into space. To an outside observer, it appears as though the black hole is emitting radiation. This is known as Hawking radiation, first described by Stephen Hawking. At first, this radiation is incredibly faint. A massive black hole emits so little energy that it is practically undetectable. Its temperature is extremely low, far colder than the already cold background of the universe. For long periods, it seems unchanged, silent, stable, and eternal. But the process never stops. With each tiny emission, the black hole loses a small amount of mass. This loss is so gradual that it takes unimaginable lengths of time to become noticeable. Yet over trillions upon trillions of years, the effect accumulates. The black hole begins to shrink. One of the most fascinating truths about this process is how it accelerates over time. As a black hole loses mass, its temperature increases. This means it emits radiation more quickly, leading to further mass loss. It is a slow beginning, followed by a gradual acceleration, and eventually a rapid conclusion. But rapid, in this context, is still relative to cosmic timescales. For most of its life, a black hole fades almost imperceptibly. Another quiet detail lies in the sheer duration of this process. A black hole with the mass of our Sun would take around 10 years to evaporate completely. A supermassive black hole, like the one that once sat at the center of a galaxy, could take up to 10^1 years or more. These numbers are so vast that they stretch beyond intuitive understanding. They represent a future so distant that everything we have discussed so far, the fading of stars, the drifting of galaxies, even the decay of matter, occurs long before black holes reach their final stages. In this sense, black holes are the last witnesses of the universe's history. They outlast stars. They outlast galaxies. They outlast matter itself. And yet, they too are temporary. As the universe continues to expand and cool, black holes become increasingly isolated. With no surrounding matter to interact with, they drift in near-perfect darkness, slowly losing mass through radiation. There are no dramatic events, no sudden changes. Just a steady, quiet fading. Another fascinating aspect is how the radiation emitted by black holes contributes to the overall energy of the universe. Though incredibly faint, this radiation becomes one of the last remaining sources of energy in a cosmos that has otherwise grown cold and still. It is a final whisper of activity, a reminder that even in the deepest silence, processes continue. There is also a subtle interplay between black hole evaporation and the expansion of the universe. As space stretches, the radiation emitted by black holes spreads out, becoming even more diluted. The energy released is not concentrated or impactful. It simply adds to the background, fading into the vastness of space. Nothing builds from it. Nothing changes because of it. It simply exists, and then disperses. Another quiet truth is that not all black holes evaporate at the same rate. Smaller black holes, if any remain, evaporate more quickly due to their higher temperatures. Larger ones persist for far longer, fading at an almost imperceptible pace. This creates a staggered timeline of disappearance. Smaller black holes vanish first. Larger ones follow much later, until eventually only the most massive remain, and even they begin to shrink. As your thoughts drift through this era, imagine a universe where the only remaining structures are these slowly evaporating black holes. No stars, no galaxies, no matter, just isolated points of mass, each quietly losing energy over immense spans of time. The darkness is complete. The silence is profound. And yet, there is movement, subtle, continuous, and inevitable. Another fascinating detail lies in the nature of the final stages of evaporation. As a black hole becomes very small, its temperature rises significantly. It begins to emit radiation more rapidly, losing mass at an increasing rate. What was once a slow process becomes more noticeable. The black hole, which existed for an almost infinite span of time, approaches its end more quickly than it began. This transition, from near eternal stillness to a brief period of increased activity, is one of the most intriguing aspects of black hole physics. It suggests that even the longest-lived structures have moments of change, moments of release. But for now, in this part of the story, the black holes still remain, fading, shrinking, quietly moving toward their final moments. As the universe stretches deeper into its silent future, the last black holes approach the final stages of their existence. What began as an almost imperceptible loss of mass slowly transitions into something more noticeable, though still unfolding across immense spans of time. For most of their lives, black holes fade so slowly that they seem unchanged. But as they shrink, something remarkable happens. Their temperature rises. Their rate of energy emission increases. The quiet whisper of Hawking radiation becomes slightly more pronounced. It is still not dramatic in the way we usually imagine cosmic events. There are no blazing explosions or violent outbursts visible across the universe. Instead, there is a steady acceleration, a gradual intensifying of a process that has been ongoing for longer than almost anything else has existed. One of the most fascinating truths is that the smallest black holes are the most active in their final moments. As their mass decreases, their temperature increases sharply. This causes them to emit radiation more rapidly, losing mass faster and faster. It becomes a kind of feedback loop. Less mass leads to higher temperature. Higher temperature leads to faster evaporation. And faster evaporation leads to even less mass. This cycle continues until the black hole reaches its final stage. At this point, the black hole, once a massive silent presence, has become extremely small and extremely energetic. It releases its remaining energy in a brief but significant burst of radiation. This is often described as the final flash. It is not an explosion in the traditional sense, but rather the culmination of a process that has been unfolding over unimaginable time. A last release of energy, followed by complete disappearance. After this moment, the black hole is gone. No event horizon, no singularity, no remaining structure, just radiation, spreading outward and quickly becoming diluted in the vastness of space. Another quiet truth is that these final flashes occur at different times for different black holes. Smaller ones would have vanished earlier, while larger ones persist for far longer. The largest supermassive black holes are the last to go, their lifetimes stretching into timescales that exceed almost everything else we can tasawwur. And yet, even they cannot last forever. One by one, across the silent universe, black holes reach their final moments. A faint release of energy, a brief increase in activity, and then nothing. This marks a profound turning point in the history of the cosmos. For the first time since the earliest moments after the Big Bang, there are no longer any significant structures left. No stars, no galaxies, no remnants, no black holes. Only particles, only radiation, only space itself. Another fascinating detail is how little impact these final events have on the universe as a whole. Each black hole releases energy, but the universe is so vast and so diffuse that this energy quickly spreads out, becoming almost imperceptible. There is no chain reaction, no renewal, no new structures forming. The energy simply fades into the background. This reinforces a quiet and important truth. The universe is not cycling back into activity. It is not preparing for a new phase of creation. It is continuing its journey toward simplicity and stillness. There is also a subtle elegance in how this process concludes. Black holes, which once seemed like endpoints, regions where information and matter disappeared, are themselves temporary. They return their energy to the universe, completing a long and intricate cycle. Nothing is truly isolated. Nothing is truly permanent. Even the deepest wells of gravity eventually release what they have held. Another quiet realization is how this moment reshapes the balance of the universe. With black holes gone, there are no longer any significant concentrations of mass. Gravity, which once shaped galaxies and guided the motion of stars, becomes almost irrelevant on large scales. There is nothing left for it to organize. The universe becomes a place where the fundamental forces still exist, but have very little to act upon. Another fascinating aspect is the role of time in this final stage. The evaporation of black holes takes so long that it defines the longest era of cosmic history. When the last black hole disappears, it marks the end of the final major process in the universe. Beyond this point, there are no large-scale events left. No transformations of comparable significance. Time continues, but the story becomes almost featureless. As your thoughts drift through this final evaporation, there is a sense of quiet completion. The universe has moved through its phases: birth, expansion, structure, fading, and dissolution. Each stage has followed naturally from the one before, and now, the last remnants have quietly released their hold on existence. There is no dramatic ending, no final collapse, just a gradual fading of the last structures into a uniform, diffuse state. Another subtle truth is that the disappearance of black holes removes the last barriers to understanding the universe's contents. With no event horizons, no hidden regions, everything that exists is, in principle, accessible. though so diffuse and low energy that it is almost impossible to detect or interact with. The universe becomes transparent, but empty. There is also a gentle symmetry in this conclusion. The universe began as a simple, hot, dense state. It evolved into complexity, forming stars and galaxies. And now it returns to simplicity, cold, diffuse, and uniform. Not the same simplicity as the beginning, but a kind of quiet echo of it. As everything settles into this final state, there is a profound calm. The processes that once defined the cosmos have all played out. What remains is the steady continuation of space and time, with almost nothing left to change. And in that vast, silent expanse, the universe continues. Endlessly. Chapter 9. The possibility of cosmic rebirth. In the vast stillness that follows the fading of black holes, the universe appears to have reached its quietest state. No stars burn. No galaxies turn. No structures remain to mark the passage of time. It is a cosmos reduced to its simplest form. Particles, radiation, and space itself, stretched thin across an ever-expanding void. And yet, within this silence, a question lingers. Is this truly the end? Or could something new emerge from this near-perfect stillness? Modern physics does not offer a single, certain answer. Instead, it presents a range of possibilities, subtle, speculative, and deeply fascinating. Among them is the idea that the universe, even in its coldest and most uniform state, may still contain the seeds of transformation. One of the most intriguing concepts comes from the nature of quantum fields. Even in what we perceive as empty space, these fields are never completely still. They fluctuate, producing tiny, temporary variations in energy. These fluctuations are incredibly small, but they are real, and they persist even in the coldest imaginable conditions. This leads to a quiet but profound truth. Absolute emptiness may not exist. Even in a universe stripped of structure, something continues to happen at the smallest scales. These fluctuations raise the possibility that, given enough time, rare and unlikely events could occur. Over incomprehensibly long durations, a sufficiently large fluctuation might create a region of space with slightly higher energy density. In most cases, such fluctuations would fade almost instantly. But in extremely rare circumstances, one might grow. If such a fluctuation reached a critical threshold, it could trigger a process similar to the early moments of the universe itself, a rapid expansion of space known as inflation. This idea is connected to what physicists call quantum fluctuation and the concept of cosmic inflation. In this scenario, a tiny region of space could suddenly expand, forming a new, separate universe. Not within our universe, but branching from it. This is sometimes referred to as a bubble universe, a new region of space-time with its own properties, its own evolution, and its own potential for structure and complexity. From the perspective of our current universe, such an event would be almost impossible to detect. It would not rebuild the cosmos we once knew. Instead, it would represent the birth of something entirely new. There is also a more philosophical idea, sometimes discussed in cosmology, known as the Boltzmann brane scenario. Named after Ludwig Boltzmann, this concept suggests that in a universe that exists for an infinite amount of time, random fluctuations could occasionally produce highly ordered structures, even something as complex as a self-aware mind. These occurrences would be extraordinarily rare, but given infinite time, they become statistically possible. While this idea is more speculative and raises many questions, it highlights a key point. Even in a nearly empty universe, the laws of physics allow for the possibility of unexpected, low-probability events. Another quiet truth is that time itself plays a crucial role in these scenarios. The longer the universe exists, the more opportunities there are for rare events to occur. Processes that are effectively impossible on shorter timescales may become inevitable given enough time. This shifts our perspective on what is likely. In a universe that persists indefinitely, even the most unlikely events can eventually happen. There is also an intriguing connection between these ideas and the concept of entropy. While the universe tends toward higher entropy, a more uniform and disordered state, local decreases in entropy are not forbidden. They are simply extremely unlikely. But again, with enough time, even unlikely events can occur. This opens the door to the possibility that small pockets of order could emerge within the overall disorder. Not large, structured universes like the one we know, but perhaps tiny, transient regions where complexity briefly arises. Another fascinating idea comes from cyclic models of the universe. Some theories suggest that the universe may go through repeated phases of expansion and contraction, or that new universes are continuously being generated from old ones. While current observations suggest that our universe's expansion is accelerating and unlikely to reverse, these models offer alternative perspectives on how cosmic evolution might continue beyond the apparent end. They remind us that our understanding is still evolving, and that the future of the universe may hold surprises we cannot yet fully grasp. As your thoughts drift through these possibilities, there is a sense of quiet openness. The universe, even in its simplest and most silent state, may not be completely finished. It may still contain the potential for change, for emergence, for something new. Not a return to what once was, but the beginning of something different, something subtle, something unexpected. And in that possibility, the story continues. As the universe rests in its quiet, near-featureless state, the idea of rebirth does not arrive with certainty, but with possibility. Not a guaranteed renewal, not a cycle that must repeat, but a gentle openness within the laws of physics themselves. What remains in this era is subtle. Faint radiation, drifting particles, and the underlying quantum fields that quietly persist everywhere. These fields, even in a universe stripped of structure, are never perfectly still. They ripple with tiny, momentary variations, whispers of energy that appear and disappear without leaving a lasting trace. And yet, those whispers matter. One of the most intriguing truths is that the universe does not need large structures to create change. Even the smallest fluctuations, given enough time, can lead to unexpected outcomes. The key is not intensity, but duration. Time in this final era becomes the most powerful ingredient. With no stars to burn out, no galaxies to collide, and no major processes to conclude, the universe simply continues, indefinitely. And in that indefinite span, even the rarest possibilities begin to feel less impossible. Consider again the idea of a spontaneous fluctuation forming a tiny region of higher energy. Most such fluctuations vanish almost instantly, smoothing back into the uniform background. But in extremely rare cases, one might persist just long enough to grow. If it reaches a certain threshold, it could trigger a new expansion, a localized Big Bang, like event that rapidly inflates into its own region of spacetime. This would not rebuild our universe. It would not restore the stars or galaxies that once existed. Instead, it would create something entirely separate, a new universe with its own timeline, its own physical conditions, and its own potential for complexity. A quiet beginning, emerging from an almost silent end. Another fascinating idea is that such processes might not be unique. If the laws of physics allow for one such event, they may allow for many. Over infinite time, multiple new regions of space could form, each evolving independently. This leads to a vision of reality that is not a single isolated universe, but a kind of vast, branching system, where new universes emerge from old ones, not through intention, but through possibility. There is a certain elegance in this thought. Endings are not absolute. They are transitions. Another quiet truth lies in how these potential rebirths relate to entropy. While the overall universe trends toward maximum entropy, a state of uniform energy distribution, local decreases in entropy can still occur through fluctuations. These decreases are incredibly rare and short-lived, but they are not forbidden. In that sense, the universe never completely loses its capacity for complexity. It becomes unlikely, but not impossible. Another perspective comes from theories that suggest the fabric of spacetime itself may have properties we do not yet fully understand. Some models propose that spacetime could undergo transformations at extremely low energies or over vast timescales, leading to new phases of existence. These ideas remain speculative, but they highlight an important point. Our current understanding of physics, while powerful, may not capture the full picture of what is possible in such extreme conditions. The future of the universe may hold behaviors that are subtle, rare, and difficult to predict. There is also a philosophical dimension to this discussion. When we imagine the end of the universe, we often think in terms of finality, a last moment, a closing chapter. But the reality suggested by modern cosmology is different. There may be no final moment, no definitive end, only an ongoing process where the nature of existence changes over time, from activity to stillness, from structure to simplicity, and perhaps from simplicity to something new. Another fascinating truth is that even if no large-scale rebirth occurs, the universe still contains a kind of quiet continuity. The laws of physics remain. Space continues to expand. Time continues to flow. Existence itself does not vanish. It simply becomes more subtle, more diffuse, more difficult to perceive. There is also a sense in which the universe becomes a canvas of possibilities. Without dominant structures or ongoing processes, it is free from the constraints that once shaped its evolution. It becomes open in a quiet and abstract way to whatever the underlying laws allow. This openness is not chaotic. It is calm, balanced, full of potential but not driven by urgency. As your thoughts settle into this gentle uncertainty, there is a certain comfort in the idea that the universe is not defined by a single outcome. It does not rush toward a fixed ending. It allows for multiple possibilities, each unfolding according to the same fundamental principles. And among those possibilities is the chance, however small, for something new to begin, not as a repetition of the past, not as a restoration of what was lost, but as a continuation, in a different form, a quiet emergence from the deepest stillness. And whether or not that emergence ever occurs, the universe remains steady, expansive, and endlessly patient. Chapter 10. The silence beyond time, as the universe stretches beyond every familiar boundary, beyond stars, beyond galaxies, beyond even the last traces of matter. It arrives at a state that is difficult to describe in ordinary terms, not because it is complex, but because it is almost completely simple. This is not an ending in the way we usually imagine. There is no final moment, no last event, no point where everything suddenly stops. Instead, the universe settles into something deeper, a kind of ongoing stillness that continues without interruption. Time as a concept still exists. The fundamental laws that govern change have not disappeared. But without meaningful events, without transformations, interactions, or contrasts, the experience of time becomes almost indistinguishable from timelessness. Moments pass, but nothing marks their passage. In earlier eras, time was measured by motion, planets orbiting stars, stars evolving, galaxies colliding. These processes created a sense of flow, of progression. But now, with those processes gone, time loses its anchors. It becomes abstract, endless, unbroken. Another quiet truth is that the universe has reached a state where almost no new information is being created. In the past, every interaction, every collision, every fusion event, every emission of light added to the complexity of the universe. But in this final state, interactions are so rare that new patterns almost never form. The universe becomes informationally still, not empty of existence, but empty of change. There is also a subtle shift in how we might think about space itself. Space continues to expand, stretching distances between particles and regions even further. But with so little matter or energy left to define those distances, the concept of scale becomes less meaningful. What does it mean to measure distance in a universe where there are almost no reference points? Where particles are separated by unimaginable expanses, and nothing exists to compare one region to another. Space becomes vast beyond comprehension, and yet strangely uniform. Another fascinating detail is how the remaining particles behave. Electrons, neutrinos, and photons continue to drift, each following its path through spacetime. Their motions are simple, uninterrupted, and largely independent. There are no complex systems to bind them, no structures to contain them. They move and keep moving. Occasionally, over enormous spans of time, two particles may come close enough to interact. But such events are so rare that they barely register in the grand timeline of the universe. And what remains is the continuation of that state. Another quiet truth lies in the persistence of the laws of physics. Even in this nearly empty universe, the fundamental rules still apply. Gravity, quantum mechanics, and the expansion of space continue to operate exactly as they always have. But with almost nothing left to act upon, their effects are minimal. It is like a perfectly tuned instrument with no one to play it. There is also an interesting perspective on existence itself. In earlier times, existence was rich with variety. Stars of different sizes, galaxies of different shapes, countless interactions shaping the cosmos. But now existence becomes uniform, almost featureless, and yet it continues. Another subtle realization is that the universe does not end, because there is no mechanism within our current understanding that brings it to a halt. It does not collapse into nothingness. It does not vanish. It simply persists, forever expanding, forever quiet. This leads to a deeply calming thought. The universe is not rushing toward a conclusion. It is not counting down to a final moment. It is simply continuing in a state that becomes increasingly simple and still. There is no urgency, no finality, only continuation. As your thoughts drift through this silent expanse, imagine a universe where nothing demands attention. No light draws the eye. No motion captures the mind. Everything is steady, consistent, and unchanging. It is a kind of cosmic calm, not empty in the sense of absence, but empty of disturbance. Another fascinating truth is that in such a universe, the distinction between past and future becomes less meaningful. Without events to mark change, the direction of time, the arrow of time, loses its significance. Past and future blur into a continuous present. An endless now. There is also a gentle symmetry in this final state. The universe began in simplicity, a hot, dense state with few distinctions. It evolved into complexity, forming structures and patterns. And now it returns to simplicity once more. But this simplicity is different. It is not the potential of a beginning. It is the stillness of completion. And yet, even here the universe remains, unbroken, unfinished, continuing beyond what we can easily imagine. In this final stretch of our journey, the universe no longer feels like a place of events or destinations, but something more like a condition, a vast, quiet state where everything that once defined reality, light, motion, structure, contrast, has softened into near complete uniformity. And yet it continues. There is something deeply unusual about this stage, not because of what is happening, but because of how little is happening. The universe has not disappeared. It has not collapsed. It has not torn itself apart. Instead, it has reached a kind of steady existence that simply goes on. No beginning, no ending, just continuation. One of the most subtle truths here is that even though the universe appears empty, it is not truly nothing. Space still exists. Quantum fields still exist. The fundamental framework of reality remains intact, even if there is almost nothing left to occupy it. This means that existence, at its most basic level, persists independently of complexity. Another fascinating idea is how this state challenges our understanding of meaning. In earlier eras, meaning could be tied to events, formation, change, evolution. But in a universe where events are nearly non-existent, meaning becomes something different. It is no longer about what happens. It is about what simply is. There is also a quiet transformation in how we might think about observation. Without structures, without light, without interactions, there is effectively nothing to observe. The universe exists, but it does not present itself in the way we are used to. It is there, but silent. Another subtle truth lies in the persistence of expansion. Even now, even in this nearly featureless state, space continues to stretch. Distances between particles grow ever larger, even though those particles are already unimaginably far apart. Expansion never stops. It does not slow. It simply continues, carrying the universe into an ever more diffuse and quiet state. There is also a profound sense in which the universe has reached its most stable configuration. Without gradients, without concentrated energy, without structures to evolve or collapse, there is very little left that can change. It is not a fragile stillness. It is a stable one, a kind of cosmic equilibrium that can persist indefinitely. Another fascinating detail is how this state reframes the idea of existence itself. We often think of existence as something dynamic, filled with movement and interaction. But here, existence is quiet, static, and uniform. And yet, it is no less real. There is also a gentle realization that the universe, in reaching this state, has completed a kind of journey. Not a journey with a goal, but one shaped by the natural unfolding of physical laws. From a hot, dense beginning, to a universe filled with stars and galaxies, to a gradual fading of light and structure, and finally to this calm, uniform stillness. Each step followed naturally from the one before, nothing forced, Nothing rushed, just time and the quiet persistence of the laws that govern everything. Another quiet truth is that even in this final state, the possibility of change, however small, still exists. Quantum fluctuations may continue to occur. Tiny variations may still ripple through the underlying fields of reality. They may not lead to anything significant. They may not build new structures, but they are there, subtle reminders that the universe is never completely static. There is always some level of motion, however faint. Not that the universe ends, but that it becomes so still, so uniform, so gentle, that it feels like silence stretching on forever.